Uh, Today we will see in detail the time-dependent perturbation. We know that time-dependent Schrödinger equation is I h cross delta psi over delta t, which is equal to h psi, and where psi can be written as the linear combination of the wave function. Basis of the wave function is un. So summation over n, Cn of t, the coefficient, expansion coefficient is time dependent. Here the wave function I am separating into two parts. This is time independent, and time dependent I am separating it out. Time dependent is e power minus I E n t over h cross, where the expansion coefficient, what is Cn? Cn is uh, the how much the wave function psi n projected on the total wave function psi. That is the definition for expansion coefficient. In Dirac notation, this bra psi of n can be written as simply bra n, and you have get psi. And this Hamiltonian also we are going to separate into two parts. One is unperturbed Hamiltonian H naught, and other one is perturbed Hamiltonian multiplied by a parameter lambda. This lambda I am using to write the term in power series. So that this lambda varies from 0 to 1. 0 means no perturbation, 1 means maximum perturbation. So now you replace h, this h pi h naught plus lambda h prime, and this psi pi this one. Of course, in the psi, we have both left hand side and right hand side. You replace psi by this linear combination, both right hand and left hand side, and h this one in the right hand side. So you will get I h cross. You have to differentiate this one. There are two time dependent factor. One is Cn. So first you keep Cn as it is. Differentiate this exponential term. Of course, En is time independent. So if you differentiate this, you will get minus I over h cross En. Uh, that then that exponential term. Here already you have one un. Then now you differentiate Cn and keep this wave function as it is. So I am differentiating the expansion coefficient Cn. So I am representing that as Cn dot. Of course, you have IH cross, the left hand side. IH cross, so Cn dot, and I am keeping this term as it is, this wave function as it is. Then you come to the right hand side. So first I am plugging this here H psi, first H naught. I am plugging H naught here in the wave function. So Cn is constant, so I am plugging H naught here, and similarly here lambda H prime, second term lambda H prime, because I am separating H into two parts. So this is first part H naught, this is lambda H prime. Uh, Here you can see the minus I over h cross can be written as 1 over I h cross. So if you multiply and divide by so I squared will become minus, minus of minus will become plus, then I h cross. You will get I h cross. So this I h cross will cancel with this IH cross. This IH cross will get cancelled with this IH cross. So you will get only En here, En psi. That is, this will get cancelled, En. Then when H naught act on Un, you will get the energy wave function, energy eigenvalue En, Un. So if you compare the first term, both are equal. Here also you are getting Cn En, un exponential term. Here also Cn, En, un and that exponential term. Both will get cancelled. This will get cancelled with this. So only this second term both side exist. Then we will further reduce it. And now we have equated the second term of both left hand side and right hand side. Here, using derive notation, above equation can be written as, that is here un I am writing as get n. Here also un I am writing as get n. So take the inner product with k. So the left hand side will become bra k ket n. Right hand side bra k, because it's an operator, h prime is an operator. I am taking inner product with h prime. That is bra k h prime n. So if you consider the left hand side, this is non-zero only when n is equal to k, otherwise it is 0. So this summation will become, because we are getting only one term when n is equal to k, otherwise it will be 0. So this can be written as I h cross c dot k, because n is equal to k now. E power minus I e k t over h cross. Here I am taking this as it is. Then we will try to simplify this. So now we got this expression. You just bring this I h cross to the right hand side. So this will become I h cross power minus 1. Then this also you are going to bring, except ck dot, you are bringing other thing right hand side. When you are bringing to right hand side, this will become plus. So this exponential term will become ek minus en. So now what is ek minus en? Over in the denominator you have a h cross, you remember that. So that is h cross. E is h cross omega, so this will be equal to omega kn. This is initial energy. En is initial energy. Ek is final energy. This can be written as omega kn. So I am replacing this by e power I omega kn t. Of course, lambda, this inner product. This equation is a fundamental result of the time-dependent perturbation theory, where, as I said, omega kn is equal to ek minus en over h cross, which is called as Bohr angular frequency. So we got this expression ck dot is equal to I h cross power minus 1 summation over n cn of t e power I omega k n t lambda, this inner product. Now you can write the cn and ck dot uh, in the power series of lambda. That is cn can be written as cn 0, that is 0th order perturbation, plus lambda cn1 first order perturbation, plus lambda square cn2 second order perturbation. Since we are dealing with first order perturbation theory, we can ignore the higher order term. Similarly, ck dot, this left hand side, ck dot is can be written as ck dot 0 plus lambda ck dot 1 plus lambda squared ck dot 2. It will go on. So we are ignoring higher order term. Here you take ck dot only first two term, because we are worried only about the first order perturbation. So in the left hand side you can write ck dot of 0 plus lambda ck dot of 1. So you ignore higher order term. Similarly in the right hand side you take only these two terms. Uh, that is this first two term. Because this is first order correction, so you need not worry about second order correction. So it can be written as Cn of t can be written as Cn 0 plus lambda times Cn 1 plus it will go on. And remember that you have here one lambda. So you bring this lambda inside the bracket. So the first term will become lambda times Cn0. The second one will become lambda square times Cn1. So we will try to simplify this. Now we got this expression. Then compare the equal power of lambda. You see the left hand side. The first term is without lambda. So there is no term without lambda here in the right hand side. So ck dot 0 is equal to 0. That means the derivative is 0. That means ck is a constant here. So similarly for ck1 dot, that is this one, that is power lambda. There is only one term in lambda power. So you can write that IH cross IH cross power minus 1 summation over Cn0 of t e power I omega k n t and this inner product. Let us say the initial state. Uh, there is one here you can write as an example. There is for only one Cn of 0, it has non-zero value. For other value, it is 0. For initial condition, there will be only one wave function. Others are the projection of other wave function is negligible. So, at the initial state, all except one of the Cn0 are 0, so that the system is initially in definite unperturbed energy state. That is Cn of 0 is inner product of n with m, which is delta Kronecker delta n m. So this Cn 0 can be written as Cm of 0, initial state. And if n is not equal to n, this will be 0. All other things are 0. You will get non-zero value only for the first parameter. That is Cm of 0 e power I omega km t, because this n I am changing to m. K h prime m. Here also n I am changing to m. Now we will see what will happen. So now we got this expression ck dot of 1 is equal to I h cross power minus 1 e power I omega k and t, and this inner product of h prime with k and m. M is in initial state and k is the final state. Now in order to find the expansion coefficient, instead of finding its derivative, because the expansion coefficient gives you the probability. That is, if you take the modular square of this one, this ck, then you will get the probability. So this can be, if you integrate this e power minus omega kmt and this inner product, this you know very well that this is time part we have taken out. This is independent of time. You can take out. Not only that, this pra k and ket m are matrix element of the Hamiltonian. That is perturbed Hamiltonian H prime. which can be conveniently represented as h prime sub km. So this can be written as 1 over I h cross. Then integral is between 0 to infin tau. So we are perturbing the system at the time t equal to 0 to t equal to tau. So this is the equation used to compute the transition probability for general time dependent perturbation. Thank you very much for watching my video and supporting me continuously. Thank you very much.